Okay, hello everybody. Welcome to my talk about Git. And I know that it's getting later in the day, so maybe we try to help our blood pressure. And let me first ask you, please raise your hand if you have ever used Git. Okay, that was pretty obvious. You wouldn't have come here if you hadn't used Git before. So let's try something harder. Please raise your hand who has ever used SVN. Okay, pretty much, but not all of you. So my question is, please raise your hand who has ever heard about BitKeeper. 1, 2 was not really sure. Okay, so the fact and the number of hands that has not been raised after my question about BitKeeper really speaks a lot about the success of Git. And why I'm saying that? Because back in the 2005, BitKeeper was the source control system, version control system of Linux kernel. And all of the Linux kernel developers were using BitKeeper back in 2005. But at the beginning of the year, it turned out that they needed to stop doing that. For various reasons, you can read the whole story in the internet. But nevertheless, Linus Torvalds, he was not satisfied with neither of the then present version control systems. So at the beginning of April, he started working on Git, on developing his own version control system. And only after 4 days, he had it ready so much that he could host the source code of Git in Git itself. So Git became self-hosted then. And 2 months later, Git has already managed the production release of a Linux kernel. It was version 2.16, 2.612, if I remember properly. And the version 1.0 has been released only in December that same year. And you now see that it's nearly 20 years since Git is around with us. So you might be wondering why on earth here in 2024 on Devoxx Poland I am talking to you about Git. So my name is Mateusz Łyczek and I'm an architect at Feature Processing, a software company from Gliwice, where we work with clients from all around the world, helping them grow their business with technology. And as an architect, I am part of technical expertise community when we share knowledge between all of the architects. And besides that, I also teach Git as part of our internal training department, FP Academy. And recently, based on our expertise and our experience in internal trainings, we started offering our training services to other companies as well, Git trainings included. But given that I'm teaching Git, I have been teaching Git for 7 years around right now, I have observed a couple of things about the people who come to our trainings. So a lot of people tend to not go beyond the very basic Git commands, like git commit, git push, git merge, git pull, and that's it. And barely anyone tries to understand it better, tries to look deeper in order to use Git more consciously. And therefore, many people are anxious or even worried or afraid even to do Git commands so that they will lose their work, break the repository, and things like that. So today, I would like to tell you a few things about Git that I think are important to understand it and work with it better. So Linus, when he started working on Git, even before he started, he set himself some initial goals that he wanted to reach. He liked the distributed manner of BitKeeper, therefore he wanted the new version control system to be distributed as well because it suited his workflow, his people knew that workflow, it worked well for quite a big project that Linux kernel was at the time. He wanted it to be fast, but not only fast, he had set a very clear goals, like in numbers of seconds or milliseconds, how this new version control system, how quick it should merge branches together. And because his job back then was just receiving patches from the developers, doing code review, and merging that into the main Linux repository, it was quite important for him to be fast, and he had clear benchmarks for that. And the most important requirement that he had for us today was that he wanted Git to be secure. But for him, that Git should be secure meant that he should maintain data integrity. So whatever you commit to Git should be safe, and when you take it out, you should get exactly the same thing. No matter whether there were any read failures from the disk due to bad sectors, disk failures, anything like that, or even malicious attackers trying to tamper our repository. And how exactly did he achieve this last goal? So first, before we delve into examples of Git repositories and how commits are connected together and how it works, we need to delve a little bit deeper. And I want to say to you how Git stores information that we commit to the repository. So Git stores the information in Git objects. Git has 4 types of objects: blob, tree, commit, and tag. And for us today, the most important one would be commit. But each of these objects has its own structure. The blob ones, which hold the content of the files, are the simplest ones because they have no structure. They just take the content of a file. And the trees, commits, and tags have some structure. So whatever is in that object, we just prefix that with the name of the type, the length in bytes of the content, join that with a null sign, and calculate a hash function SHA-1 of it. And that result of that SHA-1 function is an identifier of that object. And that's why Git in its documentation calls itself as a content addressable file system, because the objects are addressed by their content, because the identifiers of the objects is determined based on the content. And that has very nice characteristics and very nice for us consequences of how Git works under the hood. Because how we know hash functions, we know that when we change the input, the output is different, which means the objects in Git are immutable. So whatever you commit to Git cannot be changed. You can create another version, something you commit to add to the repository, you will have a new object, but the old ones will still be there. So given that I've said that commits, for the user's perspective, the structure of the commit objects and to understand it is the most important in my opinion. So let's see how it looks. On the screen, you can see the structure of an example Git commit. So in the first line, you can see a word tree and an identifier and SHA-1 of a tree object, which describes the structure of directories and the content of files in our whole repository. So this represents a snapshot of content of our whole repository, which is committed in this commit into the repository. The next line with the word parent at the beginning has the identifier of the parent commit. So most of the time there's only one parent commit because this is the previous commit that were present on the branch when we did this one. But when we come to, for example, merge commits, those can have multiple parents because we are merging 2 or more even branches together. And this one single line has a very interesting consequence. Because, as I said, now that we know that the identifier of this commit will be determined by this content that we see on the slide, this identifier means that the identifier of this particular commit depends on the whole history of the whole repository up to this point, which means that we cannot change anything in that history at all to not have to change and to not have to create actually a new object with a new identifier. So the next 2 lines describe first the author of the changes that are committed in this commit. You have the name, email address, the timestamp with the time zone. And the second line is committer. the person who committed that to repository. You may wonder why those are different and how they could be different, because that's understandable. We now are used to just typing git commit, and we are the author and the committer in that commit. But back in the old days, whoever changed anything in the Linux kernel source code was sending an email with a patch of those changes to Linus. He was doing his code review. When he liked it, he would merge it to the repository and set the author as the sender of the email with the timestamp when he received that email, and he would set the committer to himself. And even today, when you do rebase, when you do cherry pick, you will end up with a different author and a different committer. Or if you were the author of the committer that you are rebasing or cherry picking, you will have a different timestamp, because that happened on a different time. And then we have an empty line, and after empty line, whatever comes after the empty line is the commit message. So there's a convention that says that the first line should have only 80 chars, and this is the title of the commit message, and then after next empty line, there comes the long content. But actually, that's just a convention. You can do whatever you like. So now that you know how commits work, let's see a real repository and how the commits are connected together and how it works, and do some real stuff and see the consequences. So to explain a little bit what you see on the screen, on the right-hand side, you will be seeing a live view of the repository in the form of a graph. Right now, there's only one node, because on the left-hand side is my console, and I will be showing you and typing commands in Git what's happening. So let's check what's in that repository. We are doing git log with one-line switch to have it short. And you can see we have just one commit with a commit message D. I will be keeping those commit messages short to not clutter the graph with the commits. And you can see here on the right-hand side, commit message D, and the first 4 characters of the ID of that commit, which will be handy later on. You can also see that we are on a branch master, and I'll tell you something more about branches later on. And given that we are more interested about commits and how Git repository work, and not especially the code that we are committing into that repository, and to speed things a little bit up, I have created a nice small script which I will be running, which just takes one parameter, creates a new file with a name containing the timestamp, so that every time it's different to not have merge conflicts and the likes. I'm adding it to staging area and committing with the commit message that comes as a parameter to that script. So whenever I type c.sh with a message, that would create a commit with that commit message. And that's it. So that's so that you know what I'm doing here, and that there is no magic behind it. So let's assume that, yeah, we are working on this repository. Let's create some more commits. And you can see on the graph that the commits that I am creating, the commit with message E and V, you can see they have arrows pointing down. Those arrows represent the parents of those commits. So the parent of the commit with commit message E is the commit with the message D. So because that was the previous commit on this branch when I created the E1. And the same for the commit V. And let's assume now that our boss came to us and said, okay, we have a great idea for a shiny new feature that our clients will definitely like and will make our company insanely rich. So we need to start working on it right away. So what are we doing? We are creating a branch for that feature. And on the graph on the right-hand side, you can see a green box with a name feature and an orange box, not necessarily a rectangle, but something different, still pointing to the commit V. And why I have represented it on the graph in this way? Because branches in Git are just pointers to commits and nothing more. So you have a graph of commits. While creating commits with the links to parents, the graph will be growing. And each and every branch that you have in your repository is actually just a pointer to one of those commits and nothing more. Even technically, behind the scenes, Git, when I created the branch, Git created a tiny file with a name feature and then SHA1 of the commit to which it should point. And that's it, nothing more. And that's why branches in Git are so lightweight and so fast, because creating a branch is just creating just a 40 or so characters file with the name of the branch. The ones who know and have used SVN know that it was not that simple in SVN. So let's assume, okay, we've created that branch feature, but nevertheless, some work on the branch master still happened. And you can see that I've created the name of our conference, Devoxx, out of the commit messages. And there are 2 X's at the end. And you can see a different commit IDs in both of them. Why is that? Because there's different structure, different content in our repository. There's different timestamp, because I created it like a few seconds afterwards. Yeah, and there is a different parent in each commit, right? So the commit message doesn't matter here at all. But commit messages are what people are paying the most attention to when they are looking through the Git log. So when we look at Git log here, about the changes, one line, we can see exactly the same history, right? So we can even see the names of the branches. This is our current one. That's why it's pointed to by the head name, because head is another special pointer which points to the branch on which we are now. So when we will check out feature branch, it would switch and start pointing to the feature branch. And we can see that the commit V is being pointed at by the feature branch. So let's now switch to the branch feature finally and create some more exciting structure than just one line of commits, because otherwise this talk would be very boring. Because I'm old-fashioned and I'm so used to typing checkout, because our colleague asked why I haven't used the command switch, which is the new command in Git. Basically, the creators of Git decided that checkout command has too many meanings, because you can do many things with it. So they decided to split it into separate commands, and switch is only one of them. There are more to do the other stuff than just changing branches to actually getting the files and so on. But my muscle memory still remembers checkout, so throughout today I will be still using checkout. Okay, so we are now on the feature branch, and yeah, we need to create some work, hard work happening at the company, developing that new shiny feature that should make the company rich. And then we all know that a lot of things happened. The economy crashed, big inflation, and so on. And our boss comes to us and says, "Okay, no client will buy that feature from us. We need to abandon the work. Let's remove everything. Forget that. We need to get to our business as usual. Come to our other stuff that we were doing before. Forget about the feature. Let's do what we have been doing before." So okay, now we are going back to the main branch, and yeah, we want to delete the branch feature. Yeah, to clean up the repository. We no longer need that code, so we delete the branch. And on the graph on the right, you can see a very interesting thing, because I have heard a number of times that people were saying, remove the old branches to free the to clean the repository, to free the resources, and so on. Whereas when you remove the branch in Git repository, the only thing that happens is, besides the arrow still bended a little because it had room right now, is that the name feature is missing. So when you remove the branch, the only thing in your local repository what happens is that pointer is removed, nothing more. The commits still are there, despite the fact that you cannot easily see them in Git log. I'm not telling that you cannot see them at all. We'll come to that later, but let's check our Git log. Okay, yeah, we are on branch master. So yeah, because Git log shows history starting from, by default, when we don't provide it with any more parameters, by default it shows the history starting from the branch that we are currently on, which means from master, and goes down through the pointers over to next commits and shows them in the order here. So we cannot see that here. We could provide a switch all to git log, which is supposed to show all of the branches that we have in our repository, the history, but that doesn't change anything in our situation because there's no branch pointing to that commit. So how can we check that the commits are there? So I'm fortunate that I have the commit ID on the screen, so I can just type 8C00 here, and now you can see the 2024 commits here. So that's an ultimate proof that I have not tampered that graph and created it artificially, but those commits are still there, which means we can easily come back to the work if we, for example, deleted that branch by accident. And I have seen in my life a couple of times already that people were re-implementing a month worth of work again from scratch because they either deleted the branch accidentally or do git reset 3 commits too far or so on, because they didn't know that they could easily come back to those commits. And because they don't know as well that Git comes with a free of charge insurance policy for all of those kinds of situations. So now that I have shown you that the commits are there, you might be wondering, when the economy gets better and our boss comes to us, okay, you remember that feature from 2 months ago that I said that you could remove? Maybe we will come to that idea again. Could you just pick up where you left off and finish that feature? And then you will start worrying, okay, how come can we come back to those changes? So it's obvious that you will not be typing down all of the IDs of the commits of the branches that you are deleting or before every reset on your notebook, right? So what you can do from Git itself and how to come to that commit IDs. To our help now comes the brilliant, I believe, command called reflog. Reflog is a command that shows us the history of changes of the branches of the pointers actually in the Git repository. So each branch, when you have created a branch, and when you do a commit, the commit object is created first, and then the branch pointer is switched from the previous commit to now the newest one, which is a change to which that pointer is pointing to. So each such change is recorded in special log file in Git, and you can see the log file through the git reflog command. And as I've said before, we have a special pointer here as well called head. This pointer has its own reflog, and this pointer has all of the changes that we have done on all of the branches, like in a chronological order. So when I type git reflog, I can see that I have checked out, moved from feature to master. I can see all of the commits that I have done on the feature branch. I can see that I have switched from master to feature to do those commits, and so on and so on and so on, back to the very initial commit in here. So what I can do now, I need to just look and search for the commit that I want the branch to point to. So I remember that the last commit had a commit message 4, and if you read the git help reflog, you could see a number of parameters that you could pass to that command to get out more information. And so now I know that this here on the left is the ID of that commit with commit message 4 that I have created on the feature branch. So I can easily type git branch feature and provide that ID 8C0066B9. Okay, and my feature branch appears again in my repository. So now we know that we have a very good insurance policy for free of charge from Git, that whatever we do, we can go back there and see all of the actions that we have done in our local repository, because reflog is only for our local repository, and do whatever we want to do with this information. There's one important thing to reflog to remember. is that Git keeps those logs only for 90 days. Well, only, or that's a good information actually, that it's even 90 days. So you have like almost 3 months to reverse any of your actions that you have done, no matter if you remember the commit ID or not. And most of the time we don't remember, because who remembers the SHA-1 of each of the commits? And those commits here also will be around only until the point there is anything referencing them. So either it is a branch, or it is another commit referencing it as a parent, or it is an entry in the ref log. So when we removed the branch from here, there was nothing else pointing to that commit. So it was considered by Git as unreachable. So after 90 days, once that reflog entries about those commits will expire, Git, while doing housekeeping in the repository, garbage collecting, only then will remove those commits. And that's why whenever you commit a password or an access key to Git repository, there's no point looking through the internet of how to remove a commit, because there's no such thing as removing commits from Git repository. You can do a reset one commit back. We'll maybe have time to show that, but the commit will still be there. So you just need to regenerate the password, you just need to invalidate that access token and so on, because those commits for 90 days will be in your local repository and in the repositories of your colleagues who have cloned your repository or pulled your changes to their local copies. So you never know who has that in the repository still. Okay, so creating branches and removing them is not really that fun stuff. We know that everybody likes rebase, right? The endless flame wars between rebasing and merging. I don't know if they all have been already fought or not, but we know that it's way more fun than just creating branches and deleting them. So let's assume that the feature, since the branch is created, has been considered finished, okay? So yeah, we're happy with that. Let's get it into production. Let's get it into master. So our developer thinks, okay, to keep the history linear, we are doing a rebase. Oh no, I need to change my branch first to the feature. And rebase, I cannot type it on master. And now we are most probably not surprised that all of the commits that were previously there on the branch feature are still there. Only the branch feature is no longer pointing to them, right? But we can see shiny for new commits with exactly the same commit messages as here, right? 2004. But I don't know if you can clearly see it on the screen, but there are different commit messages, not commit messages, different commit IDs. So you can see DFA6 on the first two and A9 EB. So because what git rebase command does, it takes all of the commits of the branch that we are rebasing that are not on the target branch, remembering them and reapplying them at the point that we tell it to in a very short story, right? So we have the 2024 commits created here. But given that this commit has a different pointer than this one here, and so on and so on and so on, given that they were created at different time by possibly a different person and so on, you now know they have different IDs, which means that when a senior developer comes and says, oh God, what you have done the git rebase and we are doing merges in our company. We cannot tamper the history and we cannot fool the history. We need to know when you started working, from which changes and so on. We need to merge those changes as they were done and not do a git rebase. Now you will know what to do. How to come back with your feature branch to a state before you do a git rebase. And the answer is, anybody knows? Sorry? Check out to commit? That might work, but I have a better answer. You could use a git reflog, right? To see, and the ID of the commit that was previous the tip of the branch feature, right? The same thing as we deleted the branch. We need to know the ID of the commit, and we now need to reset the feature branch to that point. So how to find that ID? Again, we go to git reflog, and we can see all the history of the rebase. Rebase, despite being one operation, well, that simple rebase that I performed here is just a one operation as I typed it in the console. But under the hood, Git does it in a number of steps. So it changes the pointer to master, applies the commits, and then repoints the feature to the newest commit that he has rebased. So what we need to do, okay, look through all of those rebase operations here and see, okay, we have done that rebase when we were in this state. So this ID here is really the ID of the commit of the branch that it was before. So what we need to do is to do a git reset. And what the git reset command does. I have heard on my trainings a number of times that people are afraid and they are checking the parameters correctly before they do git reset. So a lot of the people are worried about that command. And what it really does, it has like 3 versions, soft, mix, and hard. And in the soft version, the only thing that git reset does, it changes the commit to which the current branch points to. So we provide the git reset command, reset. You need to provide it with a commit ID. So you could either provide it a direct SHA-1, right? You could provide it with a name of the branch because the branch points to a commit. You can provide it with this reference of the entry in the reflog, right? So you could type head at 6, and it will now know that I mean this commit. But one important thing to remember when using those references from reflog is that they are relative. So after I do a new command and a new entry into reflog comes, that number 6 will be now, that operation will be now number 7. Because it works like a stack, right? The thing at the top of the stack is always with the number 0. So the most recent command is always has always the number 0. So let's check that out and try to do that reset in head. And for all of the PowerShell users, here you need to enclose that head at 6 in semicolon. No, that's not semicolon. I forgot the English name of this with in quotes. Yeah, thanks. So because PowerShell interprets them that characters and throws an error. So let's do the reset. And see, I have done the reset without parameters, so it was a mixed one, but we don't really have enough time today to explain in a lot of in great detail how reset works. But the most important thing for us is that the pointer of the branch changed, right? So now our feature branch is now back where it was before. So we have only the DEV commits here and 2024 in here. So that's exactly this history that it was at the beginning. So we are now prepared to do the merge to master. But before we do that, let's now mention also again one more use case. Because I've mentioned git reset, and I've mentioned that sometimes when you look through the internet about how to delete a git commit, how to remove it, sometimes the answer is that you need to do a git reset head and a dash to above, right? So the instruction is to do git reset head, something like that, right? It may be a tilde, I don't know, but it's in this case it has the same meaning. But basically it tells you, okay, just reset your branch one commit back, right? But you now know that that doesn't mean that commit gets deleted, right? What it only does, it changes the pointer, and that commit for 90 days will still be there. And you will be able to come back to it and see whatever you had there, and so on and so on. But from the point of the usual user of Git, when he runs git log, oh no, I need to do one line, he will see it as vanished, right? And when people only use git log in its simplest way to look at the history of Git repository, they may be fooled that something has vanished, is deleted, no longer there, right? So that's why I wanted to emphasize the thing with the image of the repository as a graph, because for me, and I heard from my colleagues as well, that's when we started thinking about Git repository as a graph of commits, and and thinking about all of the operations in those terms, it made life with Git a lot easier, because you now know what's really happening, and you now know that you can always use the insurance policy called Git reflog to come back to whatever place you were before, because I can now go to the reflog to see, okay, I have done the reset, so to undo it, I can reset back, right? So issue another git reset, 1. And we're back where we left off. So using this feature, you can do whatever you like. So, and git rebase is only one example. All of the other commands behave in the same way. So for example, there is one tiny switch to git commit command called amend, which even with its name suggests that it's amending something. But it's not amending the commit, because you now know that the commit objects are immutable. It's creating new ones. So we can now go and try to change maybe the commit message of the latest commit. So we have a number 4 in here. So let's put a second 4 and add that to staging area and commit. And okay, I believe I have already done this commit. So let's delve back. Okay, so you can see that now the feature is pointing to the commit with commit message 44, but that commit with the commit message 4 hasn't gone anywhere, right? It's still there. So I'm still repeating and repeating and repeating that phrase to really, for you to remember that those are immutable things that will stay with us for 90 days, and you can still go to reflog back again. So let's do that. Let's reset back, because now, no, I wanted to do that. So now, after having some fun, we can finally come back to the branch master. What happened here? Okay, I have to use the command check out status of the repository. Okay, I have a bunch of untracked files which will be overwritten by my checkout, so I can clean them. And now that's a result of me doing a git reset without a switch, because that means that I have done git reset with the mixed implied switch, which means that git resets only the staging area and left the files on the file system intact. So I have committed those files before, right? And once I did git reset, it means that Git left those files on the disk. I should have done git reset hard for them to be removed as well, because with that hard switch, reset will bring back the whole state of even the file system as it was in the commit that we are resetting to. Okay, so now I will be able to do the checkout, and we can do merge feature branch. We are happy with the commit message. And here you can see the example of the merge commit having 2 parents. And what's interesting in Git, there's not only that. I mean, we are used to merging just one thing, right? But you can very easily merge multiple branches together in one merge commit, although that's not really what we usually do. So, okay. And now that we have that merge commit in here, and the features and so on. Okay. So now I believe you understand why I have chosen the name of my talk to be graph-based increments tracker, right? Because I wanted to use the name of Git as an acronym and to really inspire you all to start thinking about Git repository as a graph of commits, right? And this graph grows bigger and bigger, and you see on the you can see on the previous example that if I did any more changes, it wouldn't fit into the screen. But our real repositories grow really quickly with those with all of those commits that we have, branches from when we deleted, and so on and so on. So when you start to think about Git repository as a graph of commits, and especially as branches, just pointers to those commits, life with Git becomes a lot easier, because we now know what's really happening under the hood, and we now know that how we can come back to any state that we have in Git before. So if you have any questions about Git or whatever you have seen during the talk, that's now a couple of minutes for us to discuss. Yes, one hand, please. Okay, so the question from the audience is which tool I have used to draw that one graph. That's a tool written by myself, inspired by one from like 7 years ago, somewhere found on GitHub. So this is really me together with ChatGPT generating a Python script that calls various Git commands to get the history. So Git logs with different switches to get the history of each branch, to get the merge commits, to even get the unreachable commits. Because that was a hard part, because I really wanted for you to show that when I delete a branch, when I do a commit amend, when I do a commit git rebase, all of the old commits stayed there, even if they are unreachable. So, okay, I'll come to that. I finished explaining the script. So the Python script is issuing Git commands and generating a graph viz string, defining the graph, and then sending that to and rendering through graph viz on the user interface with nice colors and branches. But yeah, it's very raw, I believe, not ready to share. But we can talk afterwards if you wanted. And the second question was how I have got those unreachable commits. So there is, do I have? Yes, I have. So you can do fsck command for Git to check the integrity of the repository. That will show you all of the... Git is basically now checking the correctness of the repository. And you can see that it's not listing the unreachable commits here, right? Because I need to disable reflog. So this is because, as I said before, given that there are reflog entries referencing those commits, right, for 90 days, for Git, while he will be doing git gc, so garbage collection command, because Git does garbage collection periodically whenever we issue, especially when we do pull or push and so on, we need to compact the repository. Is then removing all of the unreachable commits that has been there for more like 90 days because the reflog expired. He's then packing the files on the file system to have more compact and more efficient structure and so on. So yeah, I need to disable the reflog for the fsck method to get to those commits. Are there any more questions? Yes, I can see one and two. Okay, so the question was whether there is a possibility of actually removing a commit from Git repository. No, that I know of. I mean, you could do some hacks. So Git reflog, when you look into Git being a distributed version control system, means that you get the whole repository on your disk. And Git stores it in a directory called .git. So you can see a .git directory here. And reflog entries are stored in Git .git log. Oh, why not? .git. But because it's plural, Git logs. And you can see the name head, which means the reflog of the head pointer. So I can go to head, and okay, I need to make that bigger. So that this is a pretty simple under the hood plain text file, right? You see the old commit ID, the new commit ID, and metadata. That's it. And the entries. And after 90 days, from the top, Git will be removing those entries. So you could, for example, mess with that file to make Git think that there is no entry about that repository, but you are doing it on your own account, right? So you cannot then complain that anything breaks in Git. But even in Git book, there's a web page in the whole documentation of Git. They have some examples where they simulate some stuff by just removing the whole directory with logs to just simulate that the logs expired, and then yeah. And then after messing with that file, you need to do git gc command to force the garbage collection to force the removal of the unreachable commits. And I saw probably your colleague was before, okay? Yeah. Okay, so yeah, I can think about it, and I definitely need to clean the code because it was like created, with ChatGPT and me hacking just to get it right and nice for you. And yeah, it has some flaws. For example, if I'll not be because it's recorded. So yeah, I can think about it, and yeah, maybe once it's polished, I will publish it on GitHub. And sorry, yeah, there was one before you, and I will come to you later, please. Okay, the question is whether git gc with prune switch will cause that unreachable commits to remove. We would have to check what prune does. Okay, this all depends on what in this documentation Git means by loose objects, because that may mean that there's no reference from reflog to it. And if that's the case, then this switch will not help you. Okay, I can see a hand back there. Mm-hmm. The slide, you mean? No, this one. So I'm going to repeat the question because you have no microphone. So the question is that I've said that commit contains a pointer to parent, right? And whether it's correct to say that the merge commit has two parents because it has two arrows. Do I understood it right? Okay, so the answer is yes. The commit object contains two parents, and you can actually check that with a nice git cat file command, cat file with a -p switch and an ID of a commit 7f2d. And now you see there are two parent rows in here. Okay, I believe I saw one more hand raising. Okay, yeah, please. Sorry? Sorry, I can barely hear you. If you could come closer, maybe. That detached head? What does it mean? So detached head is a state of repository. Okay, I have 0 seconds, so I have a clearance to prolong it a little bit. Okay, so when you are on a branch, like here, so we are on a master branch now, right? And this means that the master pointer is pointing to the commit, which is considered a head of the branch, right? Git call is a head of the branch. The latest commit on the branch is called head of the branch. And if you choose to like just do git checkout or git switch in the new terms to any particular commit and not a branch, just with a direct commit ID, like for example the X one down below, B239. This operation must be run in work tree. Okay, I'm now inside the git .git directory. I need to go here. So again, check out. And now Git is telling me that I am in a detached head state, which means that the head pointer, which is telling Git repository on which branch I am at, is not pointing to a branch, so to a reference to a commit, but directly to a commit. And this means that you cannot commit anything in here, because that commit would be just in vain, right? You would be just creating commits and nothing will be pointing to it once you switch to another branch. And detached head means that you are now on something that's not a head of any branch. So that's you are on, yeah, you have your head detached because you are somewhere else. Okay, one more question. Yes. Okay. Okay, so the question was that we have git rebase, git merge, and we have also git cherry pick command. And the question is, what's the difference between cherry pick and rebase and merge? So when we do git merge, what git does, it takes, we are on one branch, right? So we have a head of that branch. We have the head of the another branch that we want to merge. So git just calculates the state of the repository, the merged state of the repository, create a merge commit with a snapshot of that calculated state. Sometimes there are conflicts. We need to solve that conflicts and especially tell Git how to calculate that merge state and create that merge commit. And that's what merge does. So effectively, it merges the state of two branches together. When we do git rebase, you notice that when I rebase the feature branch, it doesn't mean that we have those changes on master yet. We had to do a git merge feature on the master branch too, but it would be a fast forward merge because Git would be able to go with the master branch up in the history to where the feature was without any merge commits, right? Because there was no two parents to merge. It was a linear history. So it was just repointing the pointer above to include those commits. So rebase is actually changing the base where we started all of the changes of that branch, right? So when I did git rebase of the feature branch here, right, I fooled the history that, oh no, I haven't started the implementation when the state was as in the v commit. I have started it when the state was as in the x commit, right? So that's what rebase does. And only followed by a merge, it causes the changes of all of the commits from that branch, right, to be there. And merge does the same thing. When you merge two branches, all of the changes from the commits here are also in the branch to which you merged. But when you do a cherry pick, you are just picking the nicest cherries of the whole graph of commits and putting them somewhere else, right? So you're picking them one by one. So if you wanted to simulate git rebase, you would do cherry pick 4 times, right? Because you would have to cherry pick each and every commit separately. And that's the difference. But if you had just one commit, that would be the same as rebase, effectively, right? Because you would just take the commit and create a new one, right? With the same changes, but applied on a different state of repository. And yeah, that way you will have the changes there. Okay, I don't know how much we can go. So yeah, we can go. Okay, yeah. Yes, it's a configuration of the repository, so you can easily change it. Yeah. So the question was whether the reflog expiry time can be changed, and the answer is yes. But you need to do it before it expires, right? Okay, so back to my slides for a second. Thank you very much. Please remember to vote the talk and give any comments.